Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a pre-calculus lecture. I hope you enjoy it. This is the beginning of chapter 5, which is on analytic trigonometry. And 5.1 specifically is using fundamental identities. So first, let's talk about some identities that we are going to be discussing, all right? So the reciprocal identities. Now, the reciprocal identities are things like, well, cosecant is 1 over sine, secant is 1 over cosine, and cotangent is 1 over tangent. Similarly, we can say that sine is the reciprocal of cosecant, cosine is the reciprocal of secant, and tangent is the reciprocal of cotangent. All right, so those are the reciprocal identities. We also have quotient identities. Oh, that's not how you spell identities. There we go. All right. The quotient identities are, well, they're just a fancy name for saying that tangent can be written as sine over cosine, and cotangent can be written as cosine over sine. Right, these are just a whole bunch of ways to write some of these. We've also spoken about something called Pythagorean identities. Pythagorean identities. And they're all based on this first one. The sine squared plus cosine squared is equal to 1. All right. And if I take this equation and divide it by sine squared, I end up with 1 plus cotangent squared is equal to cosecant squared. All right. And if I take this equation and instead divide it by cosine, that would tell me then that tangent squared plus 1 is equal to secant squared. All right. So those are the Pythagorean identities. Another set of identities that have been mentioned, but maybe not explicitly so, are the even and odd identities. All right. And that means that there are some of these trigonometric functions that are even. And the even ones are cosine. So in other words, cosine of negative theta is equal to just cosine of theta. And secant. Secant of negative theta is equal to just secant theta. The rest are odd functions. In other words, sine of negative theta is negative sine theta. Tangent of negative theta is negative tan theta. Cosecant of negative theta is negative cosecant theta. And cotangent of negative theta is negative cotangent theta. All right, so those are the even and odd identities for all the trig functions. Lastly, we'll talk about something called the cofunction identities. Cofunction identities. And in here, what we're saying is that sine of pi over 2 minus theta is equal to cosine theta. All right. Similarly, tangent of pi over 2 minus theta would be cotangent theta. Secant of pi over 2 minus theta would be cosecant theta. Cosine of pi over 2 minus theta is equal to sine theta. Cotangent of pi over 2 minus theta is equal to tan theta. And finally, cosecant of pi over 2 minus theta is equal to just simply secant theta. All right. So those are the cofunction identities. Now, I will prove one of these. All right. And they're all based in a very similar way. They're all proved in a similar fashion. So I'll prove the first one. And here's the proof. So the first thing we need to do here is start with a right triangle. All right. So here's my beautifully drawn right triangle. There's my right angle. I'm going to call this angle here theta. All right. Now, if I look at this angle over here, let's say alpha. All right. In here, we know that alpha plus theta plus the 90-degree angle is equal to 180 degrees. All right. Which implies that alpha plus theta is simply equal to 90 degrees. So that alpha would be 90 minus theta. In radians, this would be pi over 2 minus theta. So that means that this angle over here is pi over 2 minus theta. All right. So how's that helpful? Well, if I name these sides, let's name this side A, this side B, and this side C, and I start from this angle, all right? I'm going to start from this angle, and I'm going to take sine of this angle right here. So sine of alpha, which would be just simply sine of pi over 2 minus theta. Well, from SOHCAHTOA, sine is opposite over hypotenuse, so it would be A over C. All right. Now, let's base things off of this angle, and let's look at A over C. A over C would be the adjacent over the hypotenuse based off of this angle. So this tells us now that this is equal to cosine theta. In other words, sine of pi over 2 minus theta is equal to cosine theta. And that is the proof for this very first one. The rest of these can all be proved with the same triangle here, right? All right, now let's talk about how to use some of these, all right? So, example A. Let secant of theta be equal to -7 over 5. And let tangent of theta be greater than 0. All right. So the question here is find the values of all 6 trig functions. All right. So in order to do this, we need to first recall one thing. All right. And I'll do that on the side here. So if I'm given this coordinate axis, we know that in the first quadrant, all the trigonometric functions are positive. In the second quadrant is sine as well as cosecant that are positive. In the third quadrant, it is tangent as well as cotangent that are positive. And in the fourth quadrant, it is cosine as well as secant that are positive. All right. So if we look at this, it says, well, secant has to be negative, right? But also tangent has to be positive. Now, since tangent has to be positive, that means we're working in either the first quadrant or the third quadrant. But because secant must be negative, we cannot be working in the first quadrant. We must be working in the third quadrant. So how do we deal with this now? Well, what we have to do now is we need to draw the triangle that's implied here. And the triangle that's implied is, oh, that's not it. Something like this. All right, that's a triangle that's implied, where technically this entire thing is theta, but we know that we can just use reference angles and work with this theta down here. And since secant theta is -7/5, well, secant is the reciprocal of cosine from SOHCAHTOA. Cosine is adjacent over hypotenuse, so this would be hypotenuse over adjacent. But the thing is, this negative. The question is, does the negative go on the top or on the bottom? Well, the answer is whichever isn't the hypotenuse. The hypotenuse must always be positive. So if I have here -7/5 and secant being hypotenuse over adjacent, that would tell me the hypotenuse is +7 and the adjacent is -5. All right. Now that I've got that, I can use the Pythagorean theorem to figure out this other side. All right. So if I call this side B, I know that a squared plus b squared equals c squared, so that b is equal to plus or minus the square root of c squared minus a squared, right? I'm with a squared to the other side, take the square root of both sides. That's how I get this plus or minus. At this point, we're going to say, well, this is really plus or minus the square root of c was 7, so I've got 7 squared minus -5 squared, right, because a was -5. So this gives me 49 minus 25, so plus or minus the square root of 24. 24 is divisible by 4, so we can rewrite this as 2 radical 6, because 24 is 6 times 4, and the square root of 4 is 2. Now that we've got that, notice I still have a plus or minus. Normally, with a triangle in general, we would say, well, the sides are at actual distance, so it must be a positive value. However, because we have this triangle on the coordinate axis, we have to account for possible of negative values, for the possibility of a negative value, which is exactly what we get here. And I'm just going to write it as b is equal to -√24. All right. And, well, I guess I could just write it as √2/6. This means √2 radical 6. So b is -2 radical 6. I think I said it wrong before. That's what I meant. Either way, now we can go ahead and figure out all the 6 trig function values here. So if I have sine theta, sine is opposite over hypotenuse, so that would be -2 radical 6/7. Cosine theta is adjacent over hypotenuse, so that's -5/7. Tangent theta is opposite over adjacent, so it'll be -2 radical 6/5, which is simply just 2 radical 6/5. Cosecant theta will be the reciprocal of sine, so it will be 7/-2 radical 6, which can be rewritten as the negative of 7 radical 6/12 by multiplying both the top and bottom by radical 6/radical 6. In other words, rationalizing this expression. Similarly, secant theta will be the reciprocal of cosine, which is -7/5, and cotangent theta would be the reciprocal of tangent, which would be 5/2 radical 6, which can be written as 5 radical 6/12 by multiplying both the top and bottom by radical 6/radical 6. And notice that this is consistent with what we wanted. We have secant being -7/5. That's exactly what I found. And we had tan theta being positive, and that's exactly what we found. So again, in order to solve this, we must first come up with a representative representative triangle, right, in the quadrant that's implied, and it's implied based off of this thing over here. All right. Let's do another one. Let's say that I had so let tan theta be equal to 1/3, and cosine theta be less than 0. All right. So perhaps I'll bring this down so we can look at it again. And here we go. So at this point, we're working with, well, we want tangent to be positive. Tangent is positive in the third and the first quadrant. But now we've got cosine being negative, right? Cosine being less than 0. Cosine being less than 0, well, that must be in the third quadrant once again, all right? So because we can't be in the first quadrant, because in the first quadrant, everything is positive. So when we go ahead and draw our triangle here, I didn't mean to do that. Let's do it this way in white. So when I go to draw my triangle in here, I'm going to look at, well, since tangent is opposite over adjacent, I'm going to have the opposite being 1 and the adjacent being 3, right? This over here being my theta. However, notice that, I'm just doing this to fix it a little bit. Notice that this doesn't fully make sense in the sense that we're working in a coordinate axis, so we must have negative values. But 1/3 is the same thing as saying -1 over -3. So these values being negative are still consistent with tangent being exactly 1/3. Now to figure out the value of our hypotenuse, C, our hypotenuse must always be positive, so C would be the square root of a squared plus b squared from the Pythagorean theorem. So it would be -3 squared, and that's a squared, plus -1 squared, which gives us the square root of 9 plus 1. So it's just radical 10. So C is just radical 10. And now that we've got that, we can figure out all 6 trig function values. So sine theta, opposite over hypotenuse, would be -1 over radical 10, which can be rewritten as negative radical 10 over 10. Cosine theta would be -3 over radical 10 because it is adjacent over hypotenuse. So this would just simplify to be -3 radical 10 over 10. And tan theta, which is opposite over adjacent, would be -1 over -3. But that's just 1/3, which we already knew, right? Similarly, we can figure out all the other ones. Cosecant theta would be just negative radical 10. I just take the reciprocal of this one. Secant theta would be negative radical 10 over 3. That would be this one. And lastly, cotangent theta would simply just be 3. All right. And again, we're consistent with what we wanted because we wanted cosine to be less than 0. And we definitely got that. Let's do another one. So it's example B. Example C. Let's say that I had something like, I don't know. Let's do cosine theta to be equal to 2/3 and sine theta to be less than 0. All right. And again, I'm going to bring this back down so that we can reference it as we're doing the problem. And there it is. So in here, we want cosine to be positive, all right? Well, since cosine is positive, we're either working in the first quadrant or the fourth quadrant. But since sine is negative, we cannot be working on the first quadrant. We must be on the third quadrant. So let's go ahead and draw our triangle, on the fourth quadrant. On the fourth quadrant. So what I can do here is let's draw this triangle. That's not what I wanted there. There we go. Where this angle right here is theta, and we're working with cosine. Cosine of 2/3. Cosine is adjacent over hypotenuse, so the adjacent is 2. The hypotenuse is 3. From the Pythagorean theorem, I can figure out what b here would be, because we know that b is plus or minus the square root of c squared minus a squared. That's from the Pythagorean theorem. So it would be plus or minus the square root of 3 squared minus 2 squared, which would be plus or minus the square root of 9 minus 4. So plus or minus radical 5. But since we have this on the coordinate axis, and we have this being done below the x-axis, we're going to say this is negative radical 5. All right. Now that we've got that, we can figure out everything we need, because sine theta would be opposite over hypotenuse, so negative radical 5 over 3, and that satisfies that, right side being negative. Cosine theta is adjacent over hypotenuse, but we already knew that because it was given. Tan theta would be opposite over adjacent, so negative radical 5 over 2. Cosecant theta would be the reciprocal of this, so negative 3 over radical 5, in other words, negative 3 radical 5 over 5. Secant theta would be the reciprocal of this, so 3/2. And cotangent theta would be the reciprocal of tangent, so it would be negative 2 over radical 5, which is simply negative 2 radical 5 over 5. All right. So again, with these problems, it's all about figuring out how to or which quadrant you're supposed to be working in, and finding out working out the triangle there. Now, there are other ways that we can use some of the identities that we have spoken about. All right, and it would be by doing things like, if I said simplify the following, and I've got something like cosine squared theta times cosecant theta, and then that minus cosecant theta. All right, we want to be able to simplify this, and there's a lot of different ways to go about this. All right, the very first thing I see here is that they both have a cosecant, so I can factor out cosecant, and I'm left with a cosine squared minus 1. And at that point, well, this should remind you of something. It should remind you of one of the Pythagorean identities, namely that sine squared plus cosine squared is equal to 1. So if I move this 1 over this way and the sine squared over that way, I end up with cosine squared theta minus 1 is equal to negative sine squared theta. All right, so at this point, I would say that the statement is really just cosecant theta times negative sine squared theta. But we know that cosecant is just the reciprocal of sine. So I can rewrite this as 1 over sine theta times negative sine squared theta, which simplifies simply to just negative sine theta. So I started with cosecant squared theta minus cosecant theta equals just simply negative sine theta. All right, and that's just one possibility there. Let's look at another one. Same instructions. We're going to simplify, and we're going to simplify something like this. Let's say that I've got cotangent theta times sine theta plus tan theta times cosine theta. In here, the very first thing I'm going to do is, I see that we're working with cotangent and tangent, as well as sine and cosine. So I'm just going to rewrite everything in terms of sines and cosines. Cotangent is cosine over sine. So I have cosine theta over sine theta, and that times sine theta. Tangent is sine theta over cosine theta. So I have that times cosine theta. And simplifying here, I see that these sines cancel out and these cosines cancel out. So that would give me simply cosine theta plus sine theta, and there's not really anything else that we can do there. All right, that would be as simplified as it can get there. Let's look at a harder one. Let's say that I had something like cosine theta over 1 plus sine theta minus cosine theta over 1 minus sine theta. All right, and if I want to simplify this, well, what we have to think about here is, well, what are we really working with? And what we're working with is really two fractions. And how do we add fractions? We have to come up with a common denominator. So my common denominator is going to be the product of these two, which specifically is 1 plus sine theta times 1 minus sine theta. On the numerator, to go here in the first fractions from 1 plus sine theta to this product, I had to multiply by 1 minus sine theta. So I've got cosine theta times 1 minus sine theta. All right. In the second fraction, I end up with, well, I have this negative cosine theta. But now I need to multiply it with the denominator of the other fraction, which is 1 plus sine theta. At that point, what can we do? Well, if I distribute these cosines, I end up with cosine theta minus cosine theta sine theta minus cosine theta minus cosine theta sine theta. All of this over, well, 1 plus sine times 1 minus sine. Think of this as a plus b times a minus b. Well, that's a squared minus b squared. And that's what's happening on the denominator. All right, so if I look at the denominator here and apply the product of conjugates being the difference of squares, I end up with 1 minus sine squared theta on the bottom. Now, let's look at the numerator. What cancels out? I've got cosine theta minus cosine theta. And that's it. That's all that cancels out. But what else happens in the numerator? Well, we have negative cosine theta minus cosine theta. That's going to be negative 2 cosine theta sine theta. On the bottom, I've got 1 minus sine squared. Well, recall from the Pythagorean identities that sine squared plus cosine squared is equal to 1. I want 1 minus sine squared, so that's going to give me that cosine squared is 1 minus sine squared by just moving the sine squared to the other side. So I can say here that the denominator is simply just cosine squared theta, and we've got a cosine on the top, a cosine squared on the bottom, so that's going to give us negative 2 sine theta over cosine theta, right? One of these cancels each other out. And sine over cosine is just tangent, so this is just really negative 2 tangent theta, right? Let's do one more. Let's say that I had something like let's do something with secants or cosecants. Let's say that I have 1 over, actually let's do sine theta over secant theta plus 1 minus sine theta over secant theta minus 1. And we're going to start this in a very similar way. All right. We're going to start by rewriting the denominator. We're going to have a common denominator. They both have they have a secant theta plus 1 and a secant theta minus 1. So I'm going to multiply them to get secant theta plus 1 times secant theta minus 1. And I want that parentheses after the 1. There we go. This first numerator becomes sine theta times secant theta minus 1. The second, I end up with, well, negative sine theta times secant theta plus 1. Distributing the numerator, I end up with sine theta times secant theta minus sine theta minus sine theta times secant theta minus sine theta. All of this over secant squared theta minus 1, because once again, I've got the product of conjugates, all right? So now, in the numerator, what do we see? Well, I've got sine theta secant theta minus sine theta secant theta, so those cancel each other out. What else happens in the numerator? I've got negative sine minus sine, that's negative 2 sine theta. On the bottom, I've got secant squared theta minus 1. Well, let's see what that one's going to be. Well, one of the Pythagorean identities was that 1 plus tan squared theta is equal to secant squared theta, which would mean that tan squared theta is secant squared theta minus 1. So all I really have here on the bottom is just tan squared theta, all right? But now, having tan squared on the bottom, that's the same as just having cotangent squared on top, all right? And now that I've got that, well, I can rewrite this a little bit more. We can simplify it slightly further, because cotangent is cosine squared. Well, cotangent squared is cosine squared over sine squared. And at this point, we would say, well, this is really these sines. I can cancel one of these out, so I end up with negative 2 sine theta. Excuse me, that's the one that canceled out. Negative cosine squared theta over sine theta. But then if I rewrite this as cosine theta times cosine theta and all of this over sine theta, I can group one of the cosines and sines together to rewrite it as cotangent. So this is usually negative 2 cotangent theta times cosine theta, and that really can't be reduced any further. All right, so that's in general simplifying some trigonometric expressions using some of the identities. We can also factor some trigonometric expressions. And what do I mean? Let's look at something simple. Let's say that I had something like 1 minus cosine squared of x. All right. If I let u be equal to cosine of x, well, then this statement would then simply just become 1 minus u squared. But we know how to factor this, because this would factor to be, well, it's a difference of squares, so 1 plus u times 1 minus u. In other words, since u is cosine, I can look at this as 1 plus cosine x. 1 plus cosine x times 1 minus cosine x. All right? And if you are able to go from this to this last step, that's great. You don't necessarily have to. You can just go ahead and do this u substitution. But if you can do it in one step, go for it. Let's look at another thing that could be factored. So if I've got something like 2 cosecant squared theta minus 7 cosecant theta plus 6. We want to factor this. So again, I'm going to do a u substitution. I'm going to say let u be equal to cosecant theta. So then this statement becomes 2u squared minus 7u plus 6, which at that point I can factor by doing the AC method, and I start by doing 2 times 6. Well, 2 times 6 is 12, and I need two numbers that multiply to 12 but add up to negative 7. That would be negative 2 and negative 5, right? Negative 2 plus, that's not true. Negative 3 and negative 4, there we go. Negative 3 and negative 4. Because negative 3 times negative 4 is positive 12, and negative 3 plus negative 4 is negative 7. And I'm going to write this as 2u squared minus 4u minus 3u plus 6. And as usual, notice that these two right here are just the negative 7u. Now, I'm going to factor by grouping. In the first two, I'm going to take out a 2u. I'm left with a u minus 2. In the second two, I'm going to take out a negative 3, and I'm left with a u minus 2. Because both of these have a u minus 2, I can factor it out and write it as 2u minus 3 times u minus 2. But the problem was not about u, so we had to make sure we put it back into terms of the original variable, in this case theta. So we're going to say this is 2 cosecant theta minus 3 times cosecant theta minus 2. And there we go. We factor that out. Let's do another one factoring. All right. So that was ij. Let's say that I had something like secant squared x minus 3 tan x, and then that plus 1. And in here, you might think to yourself, well, how are we going to do a u substitution if we're working with two different trigonometric functions? Well, the thing is that secant squared can be rewritten, all right? Recall that one of the Pythagorean identities was that 1 plus tan squared theta is equal to secant squared theta. So what we can do here is rewrite this as 1 plus tan squared theta, tan squared x, because we're using x here, minus 3 tan x plus 1, which simply means that we end up with tan squared x minus 3 tan x plus 2, right? Because I have 1 plus 1 because these parentheses aren't really doing anything. At this point, that's when I make my u substitution. I say let u be equal to tan x, and this statement now becomes u squared minus 3u plus 2, which is clearly factorable to u minus 2, u minus 1, right? Two things that multiply to positive 2, but add up to negative 3. But we know the problem wasn't about u, it was about your x in this case. So we're going to say that this is tan x minus 2 times tan x minus 1, all right? And that would be the factored version of that original statement, all right? So the idea here is that we're going to be using a whole bunch of different identities to rewrite some trigonometric expressions, right? And it doesn't just end here. We can do some more examples. Let's or we can hold on. Let me rephrase that. The algebra doesn't just end here. We can include more different kinds of algebra into these kinds of problems. What do I mean? So I can start with something like, and again, the instructions are just simplify, but if I have ln of the absolute value of secant of x plus ln of the absolute value of sine of x, well, we can rewrite that, right? We can simplify that. How? Well, we know from rules of logs that this would just be equivalent to you saying ln of the absolute value of secant x times sine x, because we have addition becomes multiplication. But then we know that secant is really 1 over cosine. So we have 1 over cosine times sine, and then sine and cosine, when we have it that way, can be rewritten as tangent. So this original statement of ln of secant plus ln of sine can be simplified to simply say ln of tangent, all right? So that's all the stuff to really keep in mind when we're working with trigonometric statements, all right? They can be rewritten using one of the identities or simplified otherwise. All right, that is the end of 5.1.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.